Hello everyone, I am Kyosuke Yamashita, a PhD student in Kyoto University and a research assistant in AISD, Japan. I will be talking about the problem of expanding a language class that NIZK proves in a black box manner. This is a joint work with my supervisors, Mehdi Tibouchi and Masayuki Abe, NTT, Japan. First of all, let me explain what type of research this work is. This is so-called black box construction. So, we consider if we can construct a primitive Q based on primitive P in a black box manner. More concretely, we are given an oracle that implements a primitive P. Then, we consider if we can construct Q by using this oracle. Because P is given as an oracle, we do not care how P is implemented, and that's why it is called black box. If such a secure construction exists, then we say there exists a black box construction of Q based on P. Otherwise, we say Q is separated from P. Black box work was formalized by Impagliazzo and Rudihi in 1989, who showed a black box separation between key agreement and one-way function. Since then, a lot of results have been proposed. Let me explain which primitive we consider in this work. We treat non-interactive zero-knowledge proof system, NIZK for short. An NIZK is a protocol between two parties, a prover P and a verifier V. They share a common reference string and a statement X of an NP language L. Only the prover has a witness of X and wants to prove X indeed belongs to L without revealing the witness. So, the prover creates a proof pi and sends it to verifier. Then, verifier checks the validity of the proof. An NIZK has two security properties. One is the soundness, which guarantees that it is impossible to create a proof on a false statement. The other is zero-knowledgeness, which guarantees pi does not leak anything about the witness. NIZK is one of the most central primitive in cryptography, and it has a lot of applications such as blockchain. In this work, we will consider the problem of expanding a language class that NIZK prove in a black box manner. Roughly speaking, we consider if we can construct a stronger NIZK based on weaker NIZK in a black box manner. Here, weak and strong are in terms of languages they prove. Such a black box language extension was initiated by Abe et al. In Pikeshi 2020. They showed two negative results. First, given NIZKs for languages L1 and L2 respectively, it is impossible to construct an NIZK for the language L1 or L2. Furthermore, even though given NIZKs are simulation sound, it is impossible to construct an SS NIZK for the language L1 and L2. It is important to note that a standard NIZK for L1 and L2 can be trivially constructed by running given NIZKs sequentially. Actually, this kind of languages are seen in a lot of applications such as electric voting or blockchain. So, the motivation behind the black box language extension is if we can construct a general framework for these applications. The PKC paper covers a wide class of languages, but there exists another class that this work does not cover. That is a language which includes witness relation, something like this. It says x1 belongs to L1, x2 belongs to L2, and some binary relation holds among W1 and W2. Here, any binary relation will do, such as equality or greater than. Among them, NYZKs for witness equality are used in a lot of applications. For instance, the well-known Nawo-Young construction uses an NYZK, which proves a plain text behind two different ciphertexts are the same. In blockchain, an NYZK for witness relation is used to realize contingent payment, which guarantees fair trade. So, NYZKs for witness equalities are important in cryptography, and it is not covered by the previous work. So, in this work, we will focus on NYZKs for witness equality. In particular, we consider the Nawo-Young construction, and our result is as the following. Given a CPA PKE and an NYZK for the following single ciphertext language LCPA, then there is no fully black box construction of an NYZK for the following plain text equality language LEQ. Here, LCPA is a set of ciphertext C and a public key PK, where C is a correct ciphertext and a PK. LCPA is a set of ciphertexts and public keys, where C1 is a correct ciphertext and a PK1, C2 is a correct ciphertext and a PK2, and C1 and C2 are the encryption of the same plaintext M. It is important to note that this LEQ is not covered by the previous work. In the context of the previous work, they only rule out languages something like this. It says C1 is a correct ciphertext under PK1, and C2 is a correct ciphertext under PK2. However, C1 and C2 are kind of separated, so there is no guarantee that M1 and M2 are the same. Okay, in what follows, I will explain technical aspects of this work. Because we are considering a black box construction, we should introduce oracles that implement underlying primitives. As a CPA-PK oracle, we use the oracle introduced by Gardner et al. It consists of several interfaces, and the most important interface is the encryption interface, which takes a public key, a message, and a randomness R as input and outputs a ciphertext. Actually, this interface is implemented by a random injection. Then, we introduce an oracle that almost directly implements an NYZK for the single ciphertext language. The oracle ZK consists of these interfaces: CRS generator, prover, verifier, and prover simulator. Here, the most important interface is the prover, which takes a CRS, a ciphertext, a public key, a message, and a randomness, and outputs a proof pi. Actually, this interface is implemented by a random injection as well. We showed that ZK constitutes an NIZK for the single ciphertext language, but I do not explain it in detail here. Now, let me sketch the proof of our main result. First, we assume that there exists a black box construction M of a proof system for LEQ that is zero knowledge. Then, we construct an adversary that breaks the soundness of M in the soundness game. The game is done between a challenger and an adversary who have oracle access to them. First, the challenger runs the CRS generator algorithm to obtain a CRS and sends it to the adversary. Then, the adversary proof picks a false statement, create a proof pi hat on it, and send them back to the challenger. Then, the challenger runs the verification algorithm. If this proof is accepted, then the adversary wins the game. It means the adversary breaks the soundness of M. Now, let me explain what the adversary do in this part. Here are some important observations for the adversary. Because the adversary has oracle access, it can simulate the prover algorithm inside. When the algorithm makes a query, it is actually made by the adversary. So, the adversary can control the query. Suppose the adversary is given a query X. Then, it can swap the query to another query X prime and return such a swapped answer to the algorithm. Because the encryption interface and the prover interface are implemented by random functions respectively, this algorithm cannot detect such a swapping. By following these observations, the adversary forges a proof on a false statement. The adversary creates a false statement. It generates two ciphertexts C1 and C2, which are encryption of the same plaintext M under different public keys. Then, the adversary also generates another ciphertext C1 prime, which is an encryption of another plaintext M prime. So, this is a correct statement of LEQ, but this is not. Then, the adversary runs the prover algorithm on the false statement and do the following. Suppose the prover algorithm makes this query. Because M is not a correct plaintext of C1 prime, this query should result in bot. So, the adversary swaps the query so that it contains correct plaintext M prime. Then, because M prime is a correct plaintext of C1 prime, it should result other than bot. So, the adversary returns this proof pi to the prover. The adversary repeats this until the prover outputs a proof pi. In next slide, let me explain why such a proof passes the verification. So, roughly speaking, we can say the prover algorithm runs under other correct oracles O prime and ZK prime. Let me explain about it. The left-hand side tables represent original oracles, and right-hand side represent swapped oracles. For instance, the prover interface assigns a proof pi to this query, assigns bot to this query. Of course, they are based on the result of the encryption interface. Then, because they are implemented by random injections respectively, there must be another oracle that swaps these entries. So, in other words, the prover algorithm outputs a correct proof under these swapped oracles. Because the proof is correct under these oracles, the challenger should accept such a proof, and the adversary wins the soundness game. As a conclusion, we showed that there is no fully black box construction of an NIZK for the plaintext equality language based on NIZK for the single ciphertext language. This result suggests that if we want to construct an NIZK for witness equality, we should rely on certain properties such as algebraic structures. As a future work, it remains to consider other binary relations such as range proof. I think it is also interesting to consider the case where the underlying NIZK is more specific, such as commit and proof NIZK or quasi-adaptive NIZK. Okay, that's all for me. Thank you for watching my video.